Graphing logarithms.
Now that we have a little bit of an idea what logarithms are, at least in the fact that they relate to exponential functions, what we're going to do is look at the graphs of logarithms like we do with any other function, and we'll figure out what the main characteristics are, and we'll do transformations on them. All right, to begin though, I want to keep to the idea that logarithms are inverses of exponentials. Technically, they are the inverse of exponentials with the same base. Okay, so in this case, if I have an exponential that is base 3, like 3 to the power, my logarithm is also going to be like log base 3. They have to match up that way to be inverses. Okay, so what I'd like you to begin with is go ahead and make a table of values that goes along with the exponential. Let's graph that one. We'll then talk about the graph of the logarithm in a second. All right, so here's the table completed, and as you completed that table and then we're maybe thinking about graphing it, you would have realized that there's a few values that are way too large to be graphing on the table here. That might not be too bad, but it doesn't fit what I had available. But then you're also going to have things that are like way too small to graph, like 1/27th. Come on. But there are going to be a few values in the middle that we can graph just fine. Okay, and even 1/3, you can estimate what that is. So here's a picture of the graph that goes along with it, and all I did is I plotted these 3 points to do that, and then I sort of completed the rest of it. In addition to that, you do have that horizontal asymptote at the bottom of the graph, so I went ahead and added that in there. All right, now today's focus is really about graphing the logarithms, which are the inverses of these functions. So we drew the exponential for 3 to a power. Log base 3 of x is going to be the graph of that reflected over the line y equals x. We can start to get a picture of that graph if we take the flip-flop of the same coordinates that we're able to plot here. So this first pair right here, to plot that, I'm going to use the y value first. I'm going to go 1/3 of the way out to the right, but then down -1. So I get a point here. And that's actually the reflection of this coordinate for that one. All right, next I'm going to go over 1 and up 0. So it's the reflection of this one. And then I'm also going to do a 3 and a 1. So over 3 and up 1. So that already starts to give you that sort of curve shape to it. Now keep in mind that it is reflected over that diagonal. So this part that kind of continues to go out and up is going to be over here. That's that part. And this part, which was going to that horizontal asymptote, is still going to go to an asymptote in the logarithm. It's just going to become a vertical asymptote. So it's going to get closer to that line. I'm trying to hug that line there. And you end up with a vertical asymptote. All right, and that is a picture of a logarithm based off of graphing the exponential that goes along with it. Now, what we want to do is take away from this example so then we can start to apply it to, base 2 or base 10 or whatever other base we want to do. We want to be able to apply it to other situations. So here are the key things. Aside from the fact that this is the general shape, that's what it looks like. If an exponential graph looks like this is what a logarithmic graph is going to look like. But here's some key things to keep in mind. One, it's going to have a vertical asymptote. The horizontal asymptote that comes from your exponential function is just going to be the vertical asymptote. Though I might not graph them this way, let me give you a hint of something. If you have a horizontal asymptote that would have been maybe at a 2, like elevated up here, that means that it's a vertical asymptote at 2 over here. I'm not going to actually graph it that way, but it's something to sort of keep in mind if you're looking at the exponential and its inverse logarithm together at the same time. All right, so you are going to get a vertical asymptote. That's important. All right, next, these are 3 key coordinates that you can use almost all the time to graph, right? And they're the same 3 that I've identified over here, right? In your exponential, we always had 0, like you use 0 as your power, you got back 1. Okay, that means that you can just flip-flop that and it becomes a coordinate for any logarithm. If you have a power of 1, like you raise 3 to the first power, or if you raise 3 to the first power, you're going to get back 3. So you can actually just flip that. So whatever your base is, you can do that and then graph it with a 1. Okay, and then also you get this coordinate here, that -1 and that reciprocal. You can flip that backwards. So if you use the reciprocal of your base as your x value and then -1, that will apply to a point as well. So these will give you generally 3 key coordinates. Sometimes you can't even do all 3 of them, but you can take from those and that'll get you going along with the vertical asymptote. Example number 1 is going to address the translations that we could have in graphs. Remember that any number that is closely attached to the x value that's being added or subtracted is going to be some horizontal movement. Okay, and if you have a +3, that means that it's going to go in the negative direction 3. Anything that you have at the end that is being added or subtracted is going to be, it's like a final piece to any function. That's going to shift the whole thing up or down. Okay, so that +2 is going to move it up. All right, what I have is a blank grid. We are going to be graphing log base 4, and I'm going to be using some of the key points. But what I'm going to do is use the translation pieces to move, in a sense, the grid around. And you've seen me do this with all the other functions preceding this one, so there's no reason not to apply the idea here. Okay, the original function would have a vertical asymptote at the y-axis. That would be there. Okay, but since we've got a +3, that means that everything's going to shift to the left 3 units. So at -3, you're going to get your vertical asymptote. Okay, so in a way that's like your y-axis, but it's actually an asymptote. All right, the +2 is going to elevate everything 2 units, so I'm also going to draw a line that's here. Now this, you got to be careful about this line here. I'm going to draw it as a solid line. It doesn't really exist as part of the graph in any way. Like the asymptote, you know how that works. This is not part of the graph, but what I'm using it to do is kind of reset where everything is, and it tells me basically that this spot is going to be treated like my origin. So now what I'm going to do is grab like my key coordinates. My key coordinates are going to be the 1, 0. It's going to be the b value, the base 1, so that's base 4, so 4, 1. Then you also get the reciprocal coordinate, which is the reciprocal of the base and a -1. These are the 3 key coordinates, let me show them to you again, that we can use for graphing. Okay, now all I'm going to do is apply these coordinates as if that were the origin. Okay, so 1, 0 just means that I've got a point that's here. So instead of it being at 1, 0, it's coming from where these lines intersected, and it's going to be at that spot. All right, then 4, 1, again, treat that like the origin. You're going to go over 4 and up 1. You get a point there, and then you've got 1/4 and -1, so just a tap hit over, but then down to there. That should give you enough that you can create the graph. You've got your asymptote that you get to sort of follow along. And these are a bit tough to draw. I'll just draw the arrow there, so I don't have to try too hard, but there's a picture of your graph. And I guess what would be helpful maybe is also spend a little bit of time just thinking about like what the graph would look like without the translation, but just considering the base, like what does base 2 look like? What does base 3 look like? What does base 4 look like? And then kind of just moving them around with the translations. All right, some questions to answer here. The domain and range that goes along with this. The domain, it is bounded at that vertical asymptote. So you get an open parentheses at -3, and it goes on to infinity, goes further that way. So there's this bounding on one side for the domain. The range values, it actually can go as low as -infinity. In this part, it does not go into an asymptote, but it's always getting a little bit taller. So that one is also going to infinity, but positive infinity. So range is all real numbers, but the domain will be bounded. Usually bounded on this way, unless we decide to flip the graph for some weird reason that direction. Now, you should also take a little bit of time and go back and look at exponentials and think about the domain and range for those. For exponentials, the domain was all real numbers, but the range was the one that was bounded in a certain, either on top or bottom, depending on how we flip it or not. All right, example number 2. The main thing that we're going to be bringing in here is an a value. Okay, remember that a factor that sits in the front of everything is going to vertically stretch and compress the graph. So we deal with that part close towards the end of it, but, not at the beginning for sure. All right, what I have done so far, because I had the x plus 4, and that was closely attached to the x, it's inside the parentheses with it, that is going to be a horizontal shift to the left direction 4 units. So went over to -4 and drew that vertical asymptote. Okay, now I don't have any vertical shifting, no adding or subtracting at the end, so I went ahead and highlighted the x-axis. So we know it's there, but I think for consistency, it's good to make sure that I at least draw both of them. All right, so this is my makeshift origin that I'm going to measure everything from. All right, what we do next is we think about our key coordinates. Okay, and our key coordinates include 1, 0. It includes your base and 1. The base for this, because you can't see one, right? There isn't any subscript there. That means that this is base 10. So you have 10, 1. Then your third coordinate is going to be that reciprocal coordinate, so 1 over 10 with a -1. Okay, so these would be the points that I would graph if I didn't have that 4 that was there. So from this point, I would put a dot right there. That'd be the 1, 0. I'd also have to go over 10 and up 1, which would be all the way over here, and then up 1 for that spot. All right, and then this one's almost meaningless because you only go out 1/10 of a unit and then down 1, so you don't really get anything out of that. But because we have the 4, you're going to magnify the vertical part of it. You're going to be multiplying these numbers by 4 for the graphing part. Okay, now in the first, that doesn't really change anything, does it? Right, so we go over 1 and we're supposed to go up 0, and then 0 times 4 is still going to be 0. So you're still at that point. That one didn't change. The one that you're actually going to get to see change is going to be this next one here. Okay, so instead of going out 10 units and up 1 to graph that, you're going to go over 10 units and up 1 times 4, which is going to be 4. So you're there. The other coordinate, again, you're not going to get much out of it because you're only going 1/10 of a unit over, so you're basically right there by the asymptote. But instead of going down -1, you're actually going to go down -4. So there's a dot, like 1/10 of the way from the asymptote, right there. You pretty much just estimate, and then if you don't even want to plot it, don't plot it. But these 2 points are definitely 2 that we can use, and oh man, see if I can even curve it that way. These are a bit hard to draw. Okay, so that's what the A value does. We still use our key points. Let's backtrack here. Do your shifting first to have a makeshift origin. Use your key coordinates to graph, but if you happen to have an A value, just multiply your Y by whatever that number is and use that pattern instead. All right, your domain is still bounded. All right, and it's an open parentheses or open interval, so you use parentheses because of the asymptote, so -4 to infinity goes on to the right forever. Your range is going to be all real numbers. It can go to -infinity, and then it can go up to positive infinity. All right, so here's the weird graph that we got to address. But I think when you dissect everything, it's not going to be as complicated as it might appear at the beginning. If the B value, your base, if it is between 0 and 1, so some fractional type number, the graph is essentially upside down. Okay, now normally we do upside down graphs by making the A value negative, and that tells you to flip it. And you can still do that. That's true. But you get this weird thing here that if just your base itself is a fraction, not even a negative number, but if it's a fraction, then the graph is actually upside down. And the reason that that works is because we go back to where logarithms came from, which is the exponential functions. So everything that we've kind of looked at so far was exponential growth and its inverse. But there's something called exponential decay. Remember this graph. There's an example like growth goes up. There was the example of exponential decay. It goes down into the asymptote. And that's when you have a B value that's some number between 0 and 1. Okay, now, if you're going to reflect that graph over the diagonal, you still have the vertical asymptote, but the asymptote, right, is over here, so it's going to reflect to that side. Your asymptote, let's see if I can even draw this right. I think I got it. There we go. Sometimes it's hard to imagine the reflections. This is what the graph's going to look like. Your vertical asymptote is still like that y-axis, unless it's been shifted, and your graph is moving into it, but it moves into it on the upper side, and then it kind of curves away from it on the bottom side. So if you take a look just at this graph, that is a logarithm upside down. That's what's happened there. All right, so we're going to be making two different graphs here. We're going to be doing the exponential decay graph. We're also going to be doing the inverse to it, which is going to be the logarithm with the 1/2 base. And then that way we can see the reflections side by side and how all this holds true. All right, key values that we could graph for the original function. You should always be looking at making the x a 0 power, or making x 0, so 1/2 to the 0 power is going to give you back 1, so you've got that point. If x is a positive 1, you're going to get back 1/2. All right, and then if x is positive 2, you're going to get 1/4, and you're going to see it move into that horizontal asymptote. All right, on the other side, if you had an exponent that was a -1, that's going to flip this over and give you 2. If you have a -2, it flips it over and squares it, which will get you to a 4. So this is k of x. It's a decay function. Okay, so it's horizontally flipped versus our growth, which means that in our logarithm, it's going to be vertically flipped from what we're used to in that. All right, and you do have the horizontal asymptote. I might just leave that out for right now. All right, logarithm though. Let's go back to just the key points though. Let's not worry about like flip-flopping coordinates here and doing it that way. Let's go back to our key coordinates. You always have, you've always got 1, 0, you've always got b1, and you've also got the reciprocal -1. You've always got those numbers. Okay, our b value is 1/2. That has nothing to do with the first coordinate. So we are still good to plot 1, 0. That coordinate we can just plot. Here, remember that your b value is a 1/2. Okay, so we're going to go out 1/2 and then up 1. And that's going to give you that coordinate. Okay, and then maybe the most interesting of all of them is this one, because you have to have the reciprocal of your b value. Now, the b value itself is a fraction, so if you do the reciprocal of the fraction, you actually just get back 2. It's, you know, if you put 1/2 in the bottom here, keep, change, flip, or whatever rule you might know, it's just going to flip it back over and give you a 2. So you get 2, -1. So that means we can go out 2 and then down 1 unit. Okay, and that'll give you 3 key points that you can get. You can do more if you want. Actually, that would be really dependent on thinking about the exponential. But based off what was mentioned before, you can see you've got that vertical asymptote at the y-axis, still there. That hasn't changed from anything before. You can't see that, but I drew an asymptote there. But it doesn't come from the bottom side. It's actually come from the top side and then curves out in that direction. Now, just to make your picture look nice and complete, we'll go ahead and draw that diagonal. They're supposed to cross at the same spot, but you know, that's a little tough to draw these lines. But you've got the reflected points, reflected points, reflected points. You got all that going on there. So if you've got a fractional base, it means that it's going to be upside down. Keep to this though. Keep to using those coordinates to plot some points, but just keep in your mind that the graph is going to have that shape, because all the other logarithms seem to be these pictures, right? You've got that asymptote and it goes up and out. Got the asymptote and goes up and then out. All right, so if you got a fractional, it's going to go down and then move the outward direction. Does it change anything with the domain and the range? Nope. You still have a bounded domain. I'll go ahead and add those on here just to do it. The domain is going to be from 0 to infinity. Right, you're bounded and then goes infinity, and your range is still going to be all real numbers.